Welcome to our introduction to remote sensing and geographical information systems, or GIS. In this video, we'll explore the fundamental concepts, history, and practical applications of these powerful tools. Whether you're a student, a professional, or simply curious about how we observe and analyze our planet from a distance, this guide will help you build a solid foundation. We'll start by defining remote sensing, then move through its history, the science behind it, and how it connects with GIS. By the end, you'll understand the basics and be ready to dive deeper into this fascinating field. Remote sensing refers to the collection of data about an object or area from a distance, typically using recording devices like cameras or sensors. It's not just about satellites; even binoculars or a simple camera are basic remote sensing tools. The key is that you're gathering information without direct contact. As technology has advanced, remote sensing now includes sophisticated satellite and aerial systems, allowing us to monitor landscapes, track environmental changes, and support decision-making in countless fields. Use of remote sensing is expanding rapidly. As new technologies emerge, the range of applications grows, from environmental monitoring to urban planning and disaster management. This video focuses on the basics, especially satellite-based remote sensing, but also touches on traditional methods like aerial photography. Understanding these fundamentals is essential for anyone interested in working with spatial data or interpreting images of the Earth. Remote sensing has a rich history. In the late 19th century, cameras were used for military reconnaissance, offering advantages over simple visual inspection. By the 1920s, aerial photography became vital for mapping and planning. World War II saw the development of sonar and radar, expanding the possibilities. Today, electronic detectors and computers allow us to collect, store, and process vast amounts of data, transforming numbers into meaningful images and insights. Remote sensing systems are generally classified as passive or active. Passive systems, like ordinary cameras, rely on existing light or radiation, such as sunlight reflected from the Earth's surface. Active systems, on the other hand, emit their own energy like radar or lidar and measure what bounces back. Each type has its strengths. Passive systems are great for capturing natural light, while active systems can operate in darkness or through clouds, making them invaluable for certain applications. Examples of passive remote sensing include photography, digital cameras, and multispectral scanners. Active systems include radar, sonar, and lidar, which use their own emitted energy to gather information. Radar is especially useful in areas with frequent cloud cover, as its waves can penetrate clouds and even some vegetation. Lidar, using lasers, is increasingly popular for creating detailed topographic maps and digital elevation models. Remote sensing relies on electromagnetic energy, which behaves both as waves and particles. The key properties are wavelength and frequency, which determine how energy travels and interacts with objects. In remote sensing, we often classify electromagnetic energy by its wavelength, from X-rays and ultraviolet to visible light, infrared, and microwaves. Most remote sensing applications focus on the visible and near-infrared regions, where the sun's energy is strongest and our eyes are naturally sensitive. Electromagnetic spectrum covers a wide range of wavelengths, from very short X-rays to long radio waves. In remote sensing, we're most interested in the visible, near-infrared NIR and thermal infrared TIR bands. Visible light is divided into blue, green, and red bands, while NIR and TIR extend beyond what our eyes can see. Different objects reflect or emit energy differently across these bands, which is the basis for identifying features in remote sensing images. All matter above absolute zero emits energy. The amount and wavelength of emitted energy depend on temperature, as described by the Stefan-Boltzmann law. The Sun at about 6,000 K emits most energy in the visible range, while the Earth at around 300 K emits mainly in the thermal infrared. This difference is crucial for remote sensing, as it determines which sensors and wavelengths are best for observing different phenomena. As radiation travels through the atmosphere, it's affected by scattering and absorption. Scattering, caused by particles in the air, diffuses light and can make distant objects appear hazy. Absorption by gases like water vapor, carbon dioxide, and ozone removes certain wavelengths, creating atmospheric windows where transmission is high. Understanding these effects is essential for interpreting remote sensing data and choosing the right wavelengths for observation. There are three main types of scattering: Rayleigh, Mie, and non-selective. Rayleigh scattering occurs with small particles and shorter wavelengths, giving the sky its blue color. Mie scattering involves particles similar in size to the wavelength, like dust or water droplets, and affects longer wavelengths. Non-selective scattering happens with large particles, scattering all wavelengths equally. Each type influences how we see and record images from above. Atmospheric gases absorb specific wavelengths of radiation. Water vapor, carbon dioxide, and ozone are the main absorbers. The regions where the atmosphere is transparent to radiation are called atmospheric windows. Most remote sensing systems are designed to operate within these windows, especially in the visible and near-infrared bands, to maximize the amount of usable data collected from the Earth's surface. When radiation reaches the Earth's surface, it can be absorbed or reflected. The proportion reflected is called albedo, and it varies by object and wavelength. For example, snow has a high albedo in visible light but much lower in the near-infrared. Understanding these differences is crucial for interpreting remote sensing images, as they help distinguish between features like vegetation, soil, and water. Different objects have unique spectral reflectance curves. Vegetation, for instance, reflects most strongly in the near-infrared, while water absorbs much of the energy in that band and appears dark. Soil reflectance depends on moisture, texture, and organic content. By analyzing these patterns across multiple wavelengths, remote sensing allows us to identify and map various surface features with accuracy. Perception of color is based on how objects selectively reflect different wavelengths. A green leaf appears green because it reflects green light and absorbs blue and red. In remote sensing, we use this principle to distinguish features, but in non-visible bands, interpretation requires training. For example, stressed plants reflect more red, making them appear yellowish. Understanding these subtleties is vital for accurate analysis. Soil reflectance is influenced by moisture, texture, and organic matter. Dry soils reflect more energy, while wet soils show dips in reflectance due to water absorption. Water itself reflects little energy, especially in the near-infrared, making it appear almost black in those images. The presence of particles in water affects its reflectance, and only surface water is typically detected by passive sensors. Aerial photography is one of the oldest and most widespread remote sensing methods. Traditionally, it used film cameras mounted on airplanes, capturing vertical or oblique images. Today, digital aerial cameras are standard, recording in multiple bands: blue, green, red, and near-infrared. These images are easy to interpret because they closely resemble what we see with our eyes, making them invaluable for mapping and survey. Aerial photographs can be panchromatic, black and white, color, or infrared. Special film emulsions and filters allow recording in different bands, including near-infrared. Digital cameras can assemble standard color or color-infrared products, offering flexibility for various applications. The choice of band combination affects how features appear and what information can be extracted from the images. Aerial photographs are central projections, meaning all rays pass through a central point in the lens. This causes radial displacement of objects, especially those with vertical extension. To use aerial photos for accurate mapping, geometric corrections are necessary. Modern digital systems and software make it easier to correct and register images to map projections, ensuring accurate spatial analysis. When two overlapping aerial photographs are taken from slightly different positions, they form a stereo pair. Viewing these together creates a three-dimensional effect, allowing for the measurement of heights and the creation of topographic maps. This technique, known as photogrammetry, has evolved from manual instruments to computer algorithms, making 3D mapping more accessible and precise. Resolution of an aerial photograph depends on the sensitivity of the film or the number of pixels in a digital camera, as well as the altitude of the flight. Modern digital aerial photos can achieve ground resolutions as fine as 1525 centimeters, allowing for the identification of very small objects. This high resolution makes aerial photography ideal for detailed local surveys. Photographic systems collect data over broad wavelength ranges, producing images that average reflected energy. Sensor-based systems like satellite sensors are tuned to specific bands, allowing for more precise discrimination between objects. With digital photography, the ability to record in multiple bands has improved, bridging the gap between traditional and modern remote sensing methods. Aerial photography is best suited for small or heterogeneous areas, when objects of interest are tiny, or when stereo and 3D interpretation will enhance results. It's especially useful when features can be easily identified in visible wavelengths. For larger or more uniform areas, or when frequent updates are needed, satellite imagery may be more practical. Satellite sensors are almost always digital, recording data as discrete values called pixels. Unlike analog photographs, which have a continuous range of shades, digital images have a fixed number of levels, typically 256 for 8-bit images. Advances in technology now allow for even higher bit depths, improving image quality and detail. Understanding this digital nature is key to working with satellite data. Satellite sensors use arrays of radiation detectors, similar to the CCD sensors in digital cameras. By using filters or splitting light with prisms, they can record specific wavelength bands. Multispectral sensors collect data in several bands, building images line by line as the satellite moves. The smallest detectable area is called the geometric resolution, and each pixel represents the average reflection from that area. As a satellite moves, its sensor scans the ground line by line, recording data pixel by pixel. These scan lines are assembled into a complete image. The size of each pixel, such as 80 by 80 meters, determines the ground resolution. Sometimes features smaller than a pixel can still influence the recorded value, making them visible as distinct patterns or lines in the image. There are two main types of multispectral scanners: scanning mirror systems and push-broom scanners. Scanning mirror systems use a rotating mirror to sweep across the ground, recording one pixel at a time. Push-broom scanners use arrays of detectors to record entire lines at once. Each type has its advantages. Push-broom scanners have no moving parts, while scanning mirrors can be more flexible in some design. Radiometric resolution refers to the number and width of wavelength bands a sensor can record. Spatial resolution is the size of each pixel on the ground. Different satellites are designed with specific applications in mind, balancing the number of bands, their width, and the pixel size. Sun-synchronous orbits ensure consistent lighting conditions for repeated observations. Before satellite images can be used, they must be preprocessed to correct for errors and distortions. Geometric correction aligns the image to a map projection, compensating for factors like satellite movement and Earth's curvature. Radiometric correction adjusts for sensor-specific errors and atmospheric conditions. These steps ensure that the data is accurate and ready for analysis. Geometric distortions in satellite images come from various sources, such as satellite altitude, speed, and Earth rotation. Corrections are applied using ground control points, distinct features with known coordinates. Resampling algorithms like nearest neighbor or bilinear interpolation assign new pixel values during correction. While these processes may slightly reduce spatial resolution, they are essential for accurate mapping. Adiametric corrections address variations in sensor response and atmospheric effects. Transforming digital numbers to absolute radiance values ensures consistency across images and sensors. Haze correction, for example, uses areas with expected zero reflectance, like water in the NIR band, to adjust pixel values. These corrections are especially important when comparing images over time or from different sources. Image enhancement methods like contrast stretching improve the visual quality of satellite images. By expanding the range of pixel values, these techniques make features more distinguishable. Other advanced algorithms can further enhance specific characteristics depending on the application. Enhanced images are easier to interpret, whether manually or by computer. Multispectral images are created by recording data in several distinct wavelength bands. Modern satellite and digital aerial images are often stored in standard formats like GeoTIFF. Since computer displays use only 3 color channels, creating a true color image involves mapping blue, green, and red bands. However, for many applications, false color composition is used, mapping near-infrared red and green bands to red, green, and blue colors, respectively. False color compositions (FCC) are widely used in remote sensing to highlight features not visible in standard color images. By mapping near-infrared to red, red to green, and green to blue, FCCs make vegetation appear red, which helps in assessing plant health and coverage. While these images may look unfamiliar, they provide valuable information for analysis and interpretation. Manual interpretation relies on human expertise to identify patterns and features in images. While computers excel at processing large datasets and classifying features using algorithms, human interpreters are better at recognizing complex patterns. In practice, a combination of both approaches is often used. Computers process and enhance images, while humans interpret and validate the results. Digital processing of multispectral data allows for advanced analysis, such as creating ratios between bands to highlight specific features. For example, the Normalized Difference Vegetation Index (NDVI) uses the red and near-infrared bands to emphasize vegetation. These digital techniques make it possible to extract more information from images than would be possible with traditional photographs. Digital images can be easily manipulated, combined with other data sources, and processed using computers. This flexibility allows for more accurate and detailed analysis, supporting a wide range of applications from environmental monitoring to urban planning. As technology advances, digital remote sensing continues to open new possibilities for understanding our world. Landsat satellite family has been a cornerstone of remote sensing since 1972. Early Landsat satellites used multispectral scanning (MSS) systems with 80-meter pixels and 4 bands. Later generations introduced the thematic mapper (TM) with 7 bands and 30-meter resolution, and the enhanced thematic mapper (ETM+ with even finer detail. Landsat's long-term, consistent data is invaluable for tracking changes on Earth. Landsat satellites have evolved to offer higher spatial and radiometric resolution. The latest versions, like Landsat 7 and the upcoming Landsat Data Continuity Mission (LDCM), provide 15-meter resolution in some bands and expanded capabilities for both terrestrial and marine applications. With a temporal resolution of 15 days, Landsat enables regular monitoring of the same area over time. Spot satellite family, launched in 1986, uses pushbroom sensor technology. Its high-resolution visible HRV sensors can record in panchromatic mode with 10-meter pixels or in multispectral mode with 20-meter pixels. The sensors are movable, allowing for both vertical and oblique recordings, and can create stereo pairs for topographic mapping. Spot's flexibility makes it a valuable resource for many applications. Spot's pushbroom sensors record entire lines at once, while scanning mirror systems like those on early Landsat satellites record 1 pixel at a time. Pushbroom sensors have no moving parts, reducing maintenance and increasing reliability. The ability to tilt the sensors allows for more frequent coverage and the creation of stereo images for 3D mapping. Remote sensing supports a wide range of applications, from environmental monitoring and agriculture to urban planning and disaster response. By providing timely, accurate, and detailed information, remote sensing helps decision-makers manage resources, track changes, and respond to challenges more effectively. Its importance continues to grow as technology advances. Geographical information systems, or GIS, are powerful tools for storing, analyzing, and visualizing spatial data. GIS integrates data from remote sensing maps and other sources, allowing users to explore relationships, patterns, and trends. By combining multiple layers of information, GIS supports better decision-making in fields like environmental management, urban planning, and public health. Remote sensing and GIS are closely linked. Remote sensing provides up-to-date, large-scale data, while GIS offers the tools to analyze and visualize this information. Together, they enable comprehensive studies of the environment, support planning and management, and help us better understand our changing world. Mastering both is essential for anyone working with spatial data. This video, we've covered the basics of remote sensing and GIS, from their history and scientific foundations to practical applications in modern technologies. Understanding these concepts is the first step toward harnessing the power of spatial data. To deepen your knowledge, consider exploring further reading or specialized courses. With these tools, you're well equipped to explore, analyze, and make informed decisions about our planet.